Hey everyone, welcome back to Holy Spirit Soapbox. This is Dan and Archie again. Last episode, we went over the cosmological argument. That was more of a philosophical than scientific type of argument, right? That we went over. Hopefully, you were able to join in on that. If you haven't, go back and listen. This episode and next episode, we'll be going over the design argument, also known as the teleological argument, which will go into more specifics about scientific or science. So, first, we want to say that these are different Christian apologetic arguments, and they're meant to give listeners a bunch of information and evidence. Now, we always highly suggest that anybody who listens to this go do more research, right? Do research on your own and then come to your own conclusions. Okay? So these arguments, Archie and I, we have talked a lot about. And these different arguments have personally helped both of us in our walks with Christ. But we always want to give the opportunity for people to agree and disagree, right? We want that to be an option. God gives us free will. We have free will to go and research on our own and come to our own conclusion. So, just want to make that little disclaimer first. Welcome back. I would love to pray if we can do that because I don't know if we did that last time. So we should pray first and then we'll pray us out later. But I'll go ahead and do that. Our Father in heaven, thank you so much for this time that we get to spend together. We thank you so much for technology. We thank you so much for giving us these opportunities to talk and get to know you more through science and through different um, pieces of evidence that you give to us. We thank you so much for giving us the mouths to speak, the ears to hear, the eyes to see. And we're just so excited to learn more about you today. So we ask that you do this so we can glorify you. In Jesus Christ's holy name, amen. All right. So welcome back. Let's just hop right into it. Tell me a little bit about the design argument. What is it all about? Because I remember us talking about it, but it's always good to get a refresher.
Sure, absolutely. So, what the design argument is, also known as the teleological argument, and teleological comes from the root word telos, which means purpose.
Mhm.
So, it's basically an argument that points out the parameters or constants in the universe that suggest a designer. They're so finely tuned that uh, it appears to be designed.
Mm.
And it
Mhm.
appears to be designed for a purpose, and that is the purpose of supporting life.
Mhm.
And it does come in two parts. So to this week, we're going to cover the area that has to do with the cosmos or the universe itself, and it kind of goes something like this: the argument. So the argument is kind of structured in this way. So uh, it says, in order for life to exist at all, the universe has to meet certain conditions. Many of these conditions are extraordinarily improbable. Their improbability is so large, in fact, that we cannot reasonably attribute their existence to pure chance. So it's reasonable to attribute the conditions to supernatural design. Now, that being said, I would like to say and point out that even the cosmological argument that we talked about last week, the design argument that we're going to talk about over the next couple of weeks here, do they prove beyond a shadow of a doubt that God exists, or prove without any doubt? Absolutely not.
Mm. Mhm.
But can science prove beyond a doubt, or even beyond a shadow of a doubt, that God doesn't exist?
Right.
Again, absolutely not.
Right.
So science has their evidence and their theories to explain the worldview, the evidence that we're going to present. So it's the
Mhm.
same evidence that science has discovered. So we're going to go over some of these scientific discoveries,
Yeah.
and you can judge for yourself what is the more plausible explanation. So we're gonna refer to it as an inference to the best explanation,
Yeah.
and we'll present the evidence. We have our views of what that evidence shows, and
Mhm.
The other side of the debate, the materialists or atheists or whatever you want to call
Mhm.
them, and they have their um, theories on what it all means and how it came to be. So
Yep.
we're just here to present that evidence and let you
Mhm.
decide uh, what you think it means.
And there's and to kind of piggyback on that, right? Like, and
Mhm.
as I said, when you research, right, when you folks go out and research, if there's anything that you come across here that is not correct, let us know, right? Like we're
Sure.
always open to hearing, okay, if this is not true, absolutely sure. Okay, we'll talk about that, right? And there's a way to talk about that in a good manner, right? Just kind of a well-rounded debate of just, okay, I get your points, here are my points, and if we can agree to disagree if necessary, right? So that's just something to all remember too. We are all human beings. We are all people,
Mhm.
and yeah, we all have different views, different experiences. So
Right.
no, that's a good point, and I appreciate that. So
Well,
yeah,
before you do go on,
sure.
I would just like to point out that the evidence that we're going to go over today, the scientific discoveries that we're going to go over today, is obviously not exhaustive. Last year we discussed, we touched on a little bit of it, just scratched the surface. We're going to go a little bit deeper today, but there's just so much of it. And if we went over all of the evidence, frankly, we'd be here for hours.
Right.
And we're going to spare you that torture of listening to us blabbing for
Yeah.
hours and
Both of
try to
us,
keep
right?
it a little bit shorter. So we will go over some points and kind of give you an idea what this is about.
Yeah. Sounds good to me. All right. Well, let's do it. So let's start similar to last episode. How did this argument come to be? What's the history behind this design or teleological argument?
So pretty much the modern scientific method has kind of developed over the last maybe 400 or 500 years. And a lot of the giants, the pioneers of the modern scientific method, people like Isaac Newton and Nicholas Copernicus, Robert Boyle, Johannes Kepler, Michael Faraday,
Mm,
and even some more recent ones like in the last 100 to 150 years, like James Maxwell and Max Planck. They were all believers, so they were Christians.
mm,
And what they believed in a God of order. And because they believed in a God of order, they believed that his creation would follow rules, like the universe that he created, it would be governed by a set of rules or laws that we had the opportunity um, to discover.
mm,
And they
mm.
developed the modern scientific methods and like telescopes and microscopes and the discoveries, the way to discover things and how to test things.
Yeah.
That was all developed to try to figure out how God created and how God sustains His universe. So
Yeah.
that was the how the modern science developed. It developed from a theistic viewpoint,
Mm,
and it wasn't until about the mid 1800s, 1859, actually, when Charles Darwin, after his voyage on the RMS Beagle, wrote his book on the origin of species and natural selection. That kind of gave a lot of fuel for the atheist movement.
mm,
And at the time, a lot of these, what we knew about the universe, what we knew about biology, the cell, for example, in Darwin's time, Darwin, they didn't really have powerful microscopes that could see what the cell was. And they pretty much thought the cell was just like a little blob of jelly or plasma or something surrounded by a membrane and didn't really do much.
mm.
So, you know, advancement has been made, and we'll get into that into the next one when we go into the dive into the biological aspect of this design argument. But as far as the cosmos, starting in the early 1900s, 1905 and 1915, when Albert Einstein advanced his theories on relativity. So he kind of refined Isaac Newton's understanding of gravity and time. So basically, he posited that time and space were one dimension, were intertwined. So he called the fourth dimension space-time.
Yep.
So what his theory did suggest, and Einstein fought this tooth and nail, he didn't want to believe it, was his theory suggested that the universe was expanding. So he knew that with the gravity that was out there, the gravity would pull everything back in and collapse on itself. And he couldn't understand why it wasn't doing that. So he posited there must be a force that was exerting outward pressure to balance out gravity. Mm-hmm. And that's when he came up with his cosmological constant that kind of made up the difference between the gravity to keep it from collapsing on itself and keep the universe static. So he did believe in a steady state universe, meaning that it was always the way it was and it hadn't changed, and that's the way it always has been. Mm-hmm. But he resisted some of the math on his theory that posited that the universe was expanding. So he fought that. And I forget the name of the scientist. It was a friend of his that was also a skeptic, but he talked to him about his constant that he says it only works for certain situations, but once you get into areas where you can see the movement and the expansion, that constant breaks down. So he urged him to go see Edwin Hubble in the early 1920s. After looking through his telescope, he found a bright star that he realized, thanks to the work of a group of women, and one woman in particular, who they were known as collectively as computers. So what they would do is they would take these plates of stars and they would kind of map out the stars and name them so they could map them across the sky. And she noticed that some of these stars would grow dimmer and brighter and dimmer and brighter. Mm-hmm. And she noticed that there was a pattern to them. So she started to map these patterns. And from there, they could determine how distances from us, how far these stars were. Mm-hmm. And Edward Hubble picked up on that, what she had started, and saw a star that seemed to be in the distance. And when he measured that star, it was a particularly bright star. So he wanted to see if it was just a large star that was far away, or a smaller star, less bright, that was a lot closer. When he measured it, he found that it was well outside of our galaxy. And then he discovered that the Andromeda galaxy was not just a nebula in the galaxy, it was actually a separate galaxy. And from there, they started to see more and more galaxies. So all of these little fuzzy patches turned out to be all galaxies. And then in 1929, he discovered that universe was expanding, and it was expanding at an accelerating rate. And how he discovered that is he discovered it through what's called the Doppler effect. You may have heard it, and I know you've seen the effects of the Doppler effect. So what the Doppler effect does, it depending on the source of sound or light, whether it's traveling towards you or away from you, and at what speed, it changes the pitch or the frequency of those waves. Mm. For example, when you hear a train coming towards you, right, or a car coming towards you, you kind of hear the pitch. It gets higher, and it goes, and then when it gets by you, it's like, right?
Yeah.
So that change in pitch is when it's approaching you, the car is actually compressing the sound waves as it moves towards you. So it gives the noise a higher pitch. And the higher the pitch is, like right in front of the car where it's compressing the most. So that's when you hear that highest pitch right as the car gets to you. And then as it goes away, it's stretching the waves, and it lowers the pitch.
That makes sense. I mean, it takes more time to get
correct
to your eardrums, right?
Exactly. So the waves are being stretched out, and it lowers the pitch. Well, light behaves the same way. Light behaves as waves. So as something is moving towards you that has light, if it's moving towards you, it compresses the light waves and it moves more towards the ultraviolet end of the spectrum.
Mm,
When it's moving away from you, it stretches those light waves, makes them longer, and it
mm,
shifts over to the red side of the light spectrum. So they call it a redshift. So what he noticed was the galaxies that were closer were redshifted a certain amount, but the farther he looked out, the farther the galaxies, the more they were redshifted, meaning the faster they were moving away from us.
mm.
So he discovered that expanding universe. So if you extrapolate backwards, they said that eventually all the matter in the universe must have been compressed into one tiny point and exploded into what we know today as matter, energy, space, and time.
Yep.
So Einstein did go see Hubble. He did see that for himself and had to finally acknowledge that, and which I think when last week I kind of mentioned it. It's what caused Einstein to say about his cosmological constant. It was the biggest blunder of his life. He just
Right.
refused. He refused to accept what his theory was showing him.
Yep.
So that eventually that developed into the Big Bang. So what physicists and scientists did from there is they were looking for evidence to prove their theory. There were other theories that were coming out. This is when a lot of the quantum field theories were coming out, and string theory was starting to make its way, like later on, 60s, 70s. The theory of inflation started to come out. And they had competing theories, and there were some scientists that refused to accept the Big Bang. They were trying to find other theories.
Hmm.
So the physicist says, okay, so if there was a Big Bang or a rapid expansion at the beginning of everything, we should be able to see the echo of that. And it would be like a microwave background radiation. They should be able to detect that.
So hold on, real quick. Were you saying that the Big Bang Theory was not widely accepted initially?
It was not.
Is
It was
it
not
was
until
not
the
widely
60s,
accepted?
right?
Okay.
So it was
Wow.
finally accepted. For example, like Einstein theory, when he first came out with his theories on relativity, they did experiments that started to show, to try to show whether the theory was valid or not.
Yep.
And the more that we've done those experiments, the more that it's
Mm,
shown that we've gotten closer to showing that Einstein was right.
mm,
One of the biggest ones is, for example, when he showed that gravity was like acceleration. And his big experiment was that, imagine being in an elevator. Now, if you're in an elevator and it's accelerating upward at a rate of 9 meters per second squared, which is the rate that we fall to Earth due to gravity, how would
mm,
you be able to tell if it was acceleration or gravity? There would be no difference, right?
mm,
So
mm,
now he imagined, let's say you put a hole in the side of this elevator, so a beam of light could be shot forward. So during acceleration, by the time the beam reached the other end, you could see the beam curve down because the elevator
mm.
was moving up. So
I
he
have heard
posited
about
if it
this.
was the
Yep.
same force,
Yep.
then light should bend around massive objects like stars or black holes or galaxies. So they
Mm,
did an experiment, and then finally in 1921, they actually showed that during a full lunar solar eclipse where it was blacked out. And they took pictures of stars that were right around the sun, and they were
mm,
out of position, the exact amount that Einstein's theory predicted. So it showed that the light from them was bending around the sun.
hmm.
So that's how they
Wow.
showed that. Another one that we use is GPS. He showed that as you get closer to a massive object, when the gravity increases,
Mm,
time slows down. So if we had like these satellites that control GPS, if they were set to the same time that we have on Earth,
mm,
we would be off by, in the course of just a couple of days, it would be a mile off because of the time difference. So time
mm.
moves much faster up in the sun, not much
Right.
faster, but milliseconds faster.
Faster than,
Yeah,
yeah.
faster than it does
Yep.
here. So it's only
Right.
milliseconds, but it is faster. And we do have computations that correct and adjust for that in order to get GPS to work when we're using our car to tell us exactly where we are.
Hmm.
So that's another way that they showed that Einstein's theories were correct.
Right.
So again, this Big Bang theory, they posited that one of the things that would show that the Big Bang did actually happen is if they could find this cosmic microwave background radiation.
Mhm.
And in 1964, a couple of radio astronomers who worked at Bell Laboratories in New Jersey, their names are Arno Penzias and Robert Wilson, they actually discovered this microwave background radiation. And I
Hmm.
think I mentioned it in the last episode. You can see that
Mhm.
when you're, in the old TVs before you had cable and you have
The
24
static.
hours. Yeah, that's static.
Mhm.
That's the microwave. You can see the microwave background radiation. So they showed that
Mhm.
they actually caught that in um, from their radio telescopes that they picked up that low hum, that static, and
Mhm.
that's how they discovered it. So that pretty much proved the theory, the Big Bang theory.
Mhm.
So from there, it's gone to, how did the expansion happen? In the 60s, right after they discovered that, I think it Carl Sagan who had his own show back then in the 60s about the
Mhm.
cosmos. And he posited that there are two criteria that are needed for life to exist. One is
Mhm.
a planet with water and an
Mhm.
atmosphere, and it would need to be the right distance from its star, from its sun, like a Goldilocks zone. So, based on what Carl Sagan said, they decided to build a vast array of radio telescopes to try to point up at the sky to see if they could hear anything that came of that. For example, like any other intelligent civilizations that were out there. They called it the search for extraterrestrial intelligence, or SETI for short.
Okay.
So they posited that was the only criteria. There were, I think they calculated 10 to the 23rd power. So that's a one with 23 zeros behind it. Number of planets that could sustain life in the Milky
Hmm.
Way galaxy.
Okay.
Well, as they searched for some kind of type of radio signals or anything for any evidence of life outside of the planet, they were just met with silence and more silence and more
Mhm.
silence. And they never picked anything up. And in that time, as science advanced and they started to look deeper at things like gravity, and they discovered atoms and the nucleus of atoms and protons and neutrons and the strong nuclear force and the weak nuclear force and the electromagnetic force. And they started to study and do experiments on those things. They started to realize that um, those criteria for life got to, next thing you know, there was like 20, then 50, then 100. And now there's over 200 of these parameters that are so finely tuned,
Hmm.
other, or life would not exist. And that's why I was saying if we covered all 200 or 300 of those today, we'd be talking for hours. So we're going to just go over a
Yeah.
couple of them just to
So
show. Yep.
you're saying that we went from about two parameters or three parameters to now hundreds
Over.
of
Yeah,
parameters just
correct.
to get a planet that can sustain life
Correct.
the way
It
this one can.
actually, yep. And it actually started right after the Big Bang. And
Hmm.
I don't recall his name, but he did measure the math for why the matter in the universe was evenly spread out. It was a lot more evenly spread out than they would have expected from just an explosion. So the math didn't
Hmm.
quite add up. Even the cosmic microwave background radiation, we actually have pictures of it. You can see it, and it's got like hot and cold spots, but we're talking hot and cold spots like a few degrees above absolute zero. But
Mhm.
that microwave background radiation, you can see the matter is pretty much spread fairly evenly across the entire universe. And
Mhm.
they didn't expect that. They expected clumping in different areas. So they were trying to figure out why this was. So that they started to do the physics and the math behind it, and they start to extrapolate back towards the singularity or the Big Bang, the moment of the Big Bang. The closest that physics can get is 10 to the negative 35th seconds after the Big Bang. So that is a fraction of a second right after the Big Bang, not a second, but right after the Big Bang,
Mhm.
point a decimal point with 35 zeros and a one after the Big Bang is as far back as they could calculate this. Before that, the physics breaks down, and they
Mm.
don't know what happened there. But what they did notice was that what made the math work and give us the universe that we actually have is that from 10 to the negative 36th of a second to 10 to the negative 32nd of a second, there was a massive inflation, that the universe inflated much faster than, I mean, many, many times, orders of magnitude faster than the speed of light.
Hmm.
Put it in perspective, in that small time frame of just, I mean, it's an imaginary, I mean, it's like a trillionth of 10 billionth of a second after the
Right.
Big Bang. The universe inflated from, let's say, the size of a cell to the size of the Milky Way galaxy.
Wow.
So it just
Hmm.
exploded in a microsecond. I mean,
Right.
smaller than a microsecond. And
Yeah.
so that's when the math was working. But they didn't understand how that expansion could have happened so quickly. So they started to come up with other theories to try to explain that. And it led to, the multiverse theory, or the many worlds hypothesis that it's sometimes called.
Hmm.
With inflaton fields, they call them. So inflaton fields would be uh, like there are many universes, and when universes clash together, it creates a new universe. In that
Hmm.
universe, uh, all these bubbles have these inflaton fields that, when they clash together, there's an instant of inflation that then cools and slows.
Okay.
But when they did the calculations on the probability of that, the probability of that is like one chance in 10 to the 1024th power. I mean, it's an enormous number that we can't even comprehend.
I mean, well, I can see somebody still saying, "Well, it's kind of like Dumb and Dumber. You're telling me there's a chance, right? Like,
Tell me there's a chance. Correct.
there is a chance in
Correct.
some form that that could happen, right? I mean,
Well, there is. It's a minute chance, but it is a chance.
right.
Uh,
But then
and,
this
and
on
this
top
is
of the first cause, now we're
correct.
starting to get a little hazy, right? So,
Correct. So these inflaton fields that they claim must be accounting for these new universes, because the odds of a universe like ours, and we'll go over a couple more, and I'll show you some of the numbers as to the odds against it happening. But
mhm.
um, the odds of the universe inflating that quickly, the odds of the universe ending up the way, just the perfect way that it is now to support life, was so astronomically improbable that they
Mhm.
developed the many worlds theory. So, well, there must be an infinite number of universes, so that
Right.
it had to have happened. We just
It
happen to live
happened.
in the one that is.
Right. Right.
However, that's what the skeptics or materialists say. We
Hmm.
say it was designed. It shows design.
Hmm.
They even Richard Dawkins said that it does have the appearance of design,
Hmm.
but it's due to random chance. So now
Hmm.
you have two competing hypotheses. It
Yeah.
looks designed, but it wasn't. And there's this multiverse of an infinite number of universes, and we just happen to live in the perfect one.
Hmm.
This is something that they can't prove. They can't see other universes. We could never test other universes. They're in different
Right.
dimensions. It's completely separated from ours. I mean, we can't even see what's going on in the next star, which is only,
Right.
you know, four
But
light years away.
physically impossible, though. I
It's
mean, either way, it's physically
at this
impossible
point, it's
to,
physically
yeah.
impossible for them to prove that theory.
Right.
So basically you have to have faith that is. So and that's one of the things that they accuse us of is we rely on faith. Well, it's a lot more faith to believe in an infinite number of universes, because again, like we talked about during the cosmological argument, they still run into the problem of an infinite regress. If there's an
Right.
infinite number of universes and they keep popping into existence all the time,
Hmm.
well, wind the clock backwards until you get to the
Right.
very first universe. And what caused that? Or does
Right.
it go on infinitely? And if it goes on infinitely and there's no starting point, then you can't have a second point, a third point, and you never get to where we are. So that's the
Right.
problem of the infinite regress.
Hmm.
So they have that problem as well. And they try to throw the same thing at us. Okay, well, if there's a creator, an all-powerful creator that created everything, who created him? And if
Right.
he's created, then who created him? And then you get an infinite regress. Well, the cosmological argument doesn't really argue that there's an infinite number of causes. It argues the opposite, that there can't be an infinite number of causes. You have to stop at a cause that is uncaused, that
Right.
always is.
Yep.
And
Exactly.
that's our side of it. So they have the burden of proof to prove that an infinite regress is possible, because that's the problem that they keep running into in a material universe.
Right.
So, and that's that. So then there's the theory of inflation and the inflaton fields, and the odds against that are so astronomical.
Right.
It's highly improbable.
Yep. Yeah. And it sounds like that is the case.
So I did see that I did mention that there are over 200 different parameters that are so finely tuned. So I think one scientist pointed out this way: imagine that you walk into a room, and you walk
Mhm.
into a room, and there's this huge electrical panel, and on it there are just, you know, dozens and dozens of these little dials, and these
Mhm.
dials are set to just the exact amount, right?
Mhm.
And that's what the universe looks like. It looks like it has been just dialed in perfectly by some kind of designer. That's how it appears, right?
Sure. Yep.
So there was a mathematician in France back in the late 1800s, early 1900s. I think he lived until about 1940 something. But in 1938, he did write a book on mathematical probabilities. And in that book, he did suggest that, and this is called Borel's Law. His name was Emile Borel.
Mhm.
And Borel's Law says that anything higher than one chance in 10 to the 50th power is highly improbable, to the point of almost impossibility. Now,
Yep.
it's not zero possibility. Like I said, like the Dumb and Dumber, you tell me there's
Yeah.
a chance, there's always a chance.
There's
But
always a
it's
chance.
so imaginably, the number is just so unimaginably huge
Mhm.
that, it's hard to comprehend how it could have possibly happened that way.
Mhm.
So
Mhm.
one professor, Professor Stephen C. Myers, what he used to do in his classroom. He used to have like a combination lock that had, like, the four tumblers, so it would have like
Mhm. Mhm.
10,000 different combinations, right?
Yep.
So he would pass it around the room, and he would say, "Okay, um, try if you can get it on the first try. Um, you get no homework for tonight, right?"
Mhm.
So he would start passing it around the room, and all the students would try, and all the students would try, and none of them could get it, except like there would be one person that would
Mhm.
actually pick the right one and open the lock.
Hmm.
Now, when that happened, all of the students immediately went, "Oh, he already or she already knew the combination. There's no way she could have guessed it, or he could have guessed it. It's one chance in 10,000. That's one in 10,000. That's
Yeah.
10, that's 10 to the fourth power, right?"
Right. Yep.
So, of course, he did. He told this one person the combination to prove that point, that
Mhm.
when somebody did guess it right, and that's just one in 10,000, that no, they must have cheated somehow, right?
Mm. Yep.
So now
Yep.
imagine a lock with 100, 10 numbers, let's say 10 numbers.
Yep.
So you got 10 billion. chances. So 1 in 10 billion. Now try to guess the combination. So if you took, like, for example, the 4 combination lock is, if you tried all 10,000 combinations to open it, guessing, and you say you chose one combination, you had 10 seconds for each combination. Every 10 seconds, you tried a different combination. It would take you over 16 hours to break that 4, to try all the possibilities on that 4-number lock.
Yep.
On a 10-number lock, if you did the same thing, one number every 10 seconds, and you did that every day, 7 days a week for 100 years, you would still only try a little more than 3% of all possible combinations.
Wow.
Right? And that's 10 to the 10th power. Okay. Now we're talking about 10 to the 50th, right? And it's not like when you go from 10 to the 4th to 10 to the 10th, it's not 6 times more combinations. It's a million times more combinations.
Right. Yeah.
Right?
It's not just because each of those have their own number
Every
of
time you add a number
twitches and
is an extra zero. So to give you an idea of how big these numbers are, 1 in 10 to the 50th or 10 to the 50th is considered so highly improbable as to be almost impossible. And that's what Emil Borel wrote in his book in 1938. Well, there are an estimated 10 to the 65th number of atoms in the Milky Way galaxy. That's a huge number. That tells you how big that number is. And there's an estimated 10 to the 80th power as the number of elemental particles in the entire visible universe. And that's just not atoms, that's the particles that make up the atoms. That's, you're breaking down protons, neutrons, electrons down into quarks and bosons and all these other
Higgs boson,
particles. Correct. So that's how many elementary particles there are in the visible universe, roughly 10 to the 80th. That's estimates, right? So this shows you just how huge these numbers are. And so some of these criteria, for example, is the second law of thermodynamics. So the anthropic principle pretty much says that things go from being ordered into chaos. So, for example, if you have a balloon with air in it, like a gas, like helium,
you pop it.
Well, yeah, it's highly organized because it's contained in this one balloon.
Right.
Once you pop it, that air spreads out. It entrophies, right? It disperses and it evens out, right? So the same thing. So the second law of thermodynamics, it's basically shows that the entropy of the universe is increasing over time, meaning it's spreading out, right? So it's moving towards a high entropy. So that means that the energy of the universe is being transferred. So it's bringing it closer to an equilibrium. So scientists believe that at some point that's going to happen. They call it the big chill, where matter and energy will be so spread out to be so equal, there'll be no more transfer of energy. Right. So to kind of highlight that, for example, if you drop, say, an ice cube into a glass of water, right? Since the water has more energy than the ice, the energy flows from the water into the ice until it melts it, right? So once it's melted, the water's energy is in equilibrium. So there's no more reason for it to transfer, right? And that's what's happening with the universe. So the universe eventually reaches that maximum entropy at some point, and thereby making it, further energy transfer no longer possible. So if we go backwards in time, we see a universe of decreasing entropy, which means that at the Big Bang, we've had an extremely low entropy universe. So mathematical physicist Roger Penrose, who was an atheist, by the way, calculated that the probability of having a low entropy universe is 1 chance in 10 raised to a power of 10 to the 123rd. So what that means, it's a 1 with 10 to the 123rd zeros. So more zeros than there are elementary particles in the visible universe.
Hmm. Wow.
Okay.
And that's way more than the 10 to the 50th, as,
Oh,
as we mentioned
absolutely.
earlier,
Yeah,
right?
yeah.
Way
It's
more
not,
than
not
that.
even close. Yeah, yeah.
Not even close. Right.
Right.
Wow.
So that's one of the, the entropic principle there that, that the low entropical entropy state of the universe is,
Mhm.
that's out of all the possible universes that could have started,
Mhm.
to have a low entropy universe would be one chance in 10 raised to a power of 10 to the 123rd. So it
Yeah.
just shows you just
Absolutely
how the
insane.
universe started is
Yeah.
highly unlikely, right?
Wow. Yeah.
So another one, for example, would be the gravitational constant versus the weak force or the weak force constant. So that's the difference between the gravity, the strength of gravity, and the strength of the weak nuclear force. And the weak nuclear force is what holds the electrons around the atom. So you have a strong nuclear force that holds the nucleus together, the protons and neutrons, and then you have a weak nuclear force that holds the electrons in orbit around the nucleus.
Right.
With regard to the cosmological constant, it regards to the expansion rate of the
Mhm.
universe. So,
Mhm.
so if the strong nuclear force, for example, or the strong nuclear force was 2% weaker, uh,
Mhm.
yeah, so the gravitational force and the weak nuclear force. So if the weak nuclear force was just slightly stronger or slightly weaker, then gravity wouldn't be able to sustain itself. It would either collapse on itself or stars wouldn't be able to form, and it would just um, it it would just spread out if it was a little bit weaker. So
Sure.
the odds of that happening is, and we're talking about a minuscule, like one part in uh, 10 billion, either stronger or weaker, and it doesn't work. It doesn't, the universe cannot sustain itself. So
Yeah.
just clicking that dial, just a fraction of a fraction of a fraction of a fraction of a percent, the
Mhm.
universe doesn't hold itself together.
Sure. And this is kind of just the beginning, right? Again, I'm going to go back to what I said at the very beginning. You have questions, you have doubts, research it, right? I know a lot of people have researched things. There are a lot of smart people out there, a lot of people that have a lot of um, the ability to put all these things together and to, just taking a lot of mathematical information or scientific information. That's an amazing thing. Research, right?
Right.
Go
Exactly.
through all this stuff yourself.
Yep.
You will see that there has to be this designer. There has to be.
And
That's just where I've come to conclusion myself.
sure. So basically, if the strong nuclear force was just 2% weaker, no elements other than hydrogen would be able to form because it would be too weak to hold the heavier elements like multiple protons and multiple neutrons together in a nucleus. And the heavy elements like carbon that make up life wouldn't exist. If it was 2% stronger, then there would be no hydrogen. All the hydrogen would be converted to helium or heavier elements. Uh,
Mm.
no hydrogen, no water, and no helium, no
Without water.
hydrogen and helium, just converting too fast, no long-term fuel for the stars, so they couldn't last long enough.
Mm.
And one last, I would just like to go is, so we have different types of stars out there. We have red dwarfs and we have blue giants and we have a bunch of stars in between, like our sun is in
Mm.
between there. So red dwarfs are basically not hot enough. They're too small and they're not hot enough to sustain life. So any planets around them would not, the daytime might get enough sun, but the nighttime would be way too cold. On the opposite side of the spectrum, a blue giant would emit too much radiation and would fry any planet or any atmosphere that's around it. So we
Mm.
couldn't live next to a red dwarf or a blue giant.
Right.
And there's a fine balance between the gravitational constant and the fine structure constant, or in other words, the electromagnetism. If the
Mm.
gravitational was slightly stronger and the magnetism was slightly weaker, we'd
Mhm.
have all red dwarfs. Now I'm talking about one part in 10 to the 23rd power. We'd have all red dwarfs. The opposite, where gravity is slightly weaker and electromagnetism is slightly stronger, we'd have all blue
Mm.
giants. Either way, life would not be possible. This is just a small sampling of the parameter, and there are over 200 of these that are just as finely tuned.
Right. And that's over 200 as of now, right? Initially it was two or three, and now it's over 200. It could be more. I mean, as we discover more and more that science starts to tell us. I mean, this is
Exactly.
just what
Sure.
God, what I will say is God through science. Like we're seeing
Right.
how God works, how God created things through science, what we call
So
science.
again, like I said, this doesn't prove that there's a God beyond any doubt,
Right.
but it does really look like it was designed to sustain life.
Right.
In the
Like you
next
said,
episode,
it
we'll look at life itself and we'll see just how much design goes into that.
right. The biology of things, right? And like you said, faith, it takes faith on both sides, on all sides.
Yep.
Everybody has faith. You have faith in something.
Yep.
So, well, I appreciate this. Let's I'll close this out in prayer and we'll go on our way.
All right.
All right, here we go. Our Father in heaven, thank you again for letting us chat today. We thank you for the technology to do this and to allow other people in the world to listen as well. We just pray that they are blessed by this and that they can just see a little bit more about of how you created things. We just want you to be glorified in all ways. We look at this and we say, wow, with all these numbers, they're absolutely insane. And we just want to continuously study you, study your heart, study your mind if we can. We'll never get to the full capacity of your mind with our little brains, but we thank you for all the things that you give us to study and just love you more. So we thank you so much for this, and we ask that you bless all of us in Jesus' name. Amen.